Welcome. So in this video we're going to talk about light and some of its properties, and we're going to calculate some of those properties such as energy and frequency. Alright, so light is made up of particles. I have to put that in quotes. Particles called photons. And the reason why I have to put particle in quotes is because light, photons, also have this wave nature. Okay. All right, so maybe for another time we can talk more about whether light or any of the observable universe, whether we are particles or we're waves. Okay, the short answer is we're a little bit of both. But when it comes to photons, this wave nature has to be discussed. As we're going to see, photons have a property called wavelength. And we're going to have to use that wavelength to calculate other useful things such as frequency or energy. And wavelength itself is an important quantity. All right, so photons have all these sorts of properties. Energy, frequency, wavelength, speed, all of these are related to each other in equations. Amplitude, we're not going to discuss so much of that today. If you have more amplitude, that just means you have more photons. And useful to know, not going to talk about it a ton, but useful to know, photons don't have any mass. They are truly massless. It's not like we're talking about an electron, which it has a very small mass, but technically it has a mass. Photons have absolutely zero mass. Any particle of light has no mass at all. Right? And there's no charge either. It's not like we're talking about protons or electrons that have charge. There's no charge involved. All right. So photons are light, also known as electromagnetic radiation. All right. Now, don't confuse this word radiation for talking about like radioactivity. When you have a radioactive material, that means that material in the process of transforming is releasing actual particles. Okay. Protons. Alpha particles, man. Recording late at night will make your brain freeze. But alpha particles, beta particles. I mean, you can have high energy photons called gamma rays, but that's coming from a material that's transformed. Here, we're just talking about photons, not radioactive materials. All right. So with that little rant out of the way, explanation. All right, so we got some light equations to discuss, all right? Pause this for a minute if you want to soak it all in, write down some notes. Let me shrink my face here. There we go. All right, so there's three main equations that are in a typical Chemistry 101 course, all right? And you could even say these two equations are the main ones because you can substitute this equation into that one and you can end up with this one. If you were to want to do that, you would rearrange this equation for this symbol I circled in blue. All right, it's called nu. You'd substitute that in and then you would get this equation. All right, but we got three equations. We have energy versus frequency, energy versus wavelength, and then we have the speed of light relationship. All right. So let's go through each of the letters or symbols first. E stands for energy. And energy, when you use these equations with these constants, those are going to be in units of, the energies will be in units of joules. All right. Then we have something called frequency. Frequency uses this Greek letter called nu. It looks a lot like a V, but it's a nu. I'll show you how to write it in a moment. And frequency is how many times something happens in some period of time. And in these equations, that period of time is going to be a second. Frequency is not in seconds. Seconds is time itself. Whereas frequency is how many times something happens in 1 second. All right, so a little bit of a difference. That second is in the denominator, the bottom. All right. So 1 over seconds for frequency, you can write it that way, s to the minus 1 power. or you can write it as the unit hertz. Me personally, I usually do that, but you do your thing. Lastly, in these equations, we have wavelength, and that's the Greek letter lambda. All right, another thing we'll have to learn how to write. And lambda, wavelength, you're going to use units of meters. All right. Now, I did write this little note here that forgetting this is the most common error. Sometimes the wavelengths are given to you in a different unit, most commonly nanometers when we're talking about visible light. All right, so if they give you something in nanometers, in order to use these equations, you'll have to convert it to meters first. If you were given something else, like an energy or frequency, and you're trying to calculate a wavelength, they might ask you for it in nanometers. So you would take your meters answer and then you would turn into nanometers. So I'll show a little bit of that in the example today. All right, the last two things I didn't point out yet. This is called Planck's constant, a lowercase h, 6.626 times 10 to the minus 34th power. And then there's two units, joules, the energy unit we talked about earlier. And then we have seconds. All right, it's joules times seconds for the units. All right, and then the other constant is the speed of light constant. All photons travel the same speed, regardless of their energy. All photons travel the same speed, and that speed is 3.00 times 10 to the 8th power meters per second. All right. If you were to measure or calculate how long it takes a photon to go from one end of the Earth to the other, it's like less than half a second. Last time I calculated. Hopefully, I still remember that correctly. Y'all can fact check me on that if you want. All right. And some people will sometimes use like the more accurate, precise version of it. I like to write 3.00 for my Chem 101 classes because for me, having a number people can remember and still be accurate with is the higher priority for me. But 2.998 is also fine here. All right. So I promised some handwriting lessons. Well, I don't know if my handwriting's award-winning or anything like that, but how do you write a nu? All right. So I like to write my nu like that. All right. It doesn't always come out the same. Sometimes you'll see like a little bit like that. But that's a nu, whereas that's a V. All right. If one of my students started writing V's instead of nus, would I really care? Me, not really. All right. But I'm not. I may or may not be your chemistry instructor, whoever, depending on who's watching this. And then we have lambda or lambda. All right. It kind of reminds me of a wave. It looks kind of like wavy, right? All right, that's how I write my lambdas, or sometimes I just kind of go like that. All right, something like that. And that's what we use for wavelength. All right, so there we go. All right, so we're about to get to our example problem, but first I thought I'd give some description of what these photon properties mean. I use words like wavelength, frequency, and what do these things actually mean. All right, and I think to help explain it, I'm going to do a comparison between a red photon and a violet photon. All right, so the first thing I'm going to tell you is that a red photon, I mean, there's different shades of red that exist, but a red photon, this particular red photon, you can get it from like a red laser pointer or something, has a wavelength for this particular shade at 650 nanometers. And then for the violet photon, you can sometimes get these violet, or sometimes they're called like purple, laser pointers, and 405 nanometers, all right? So whatever this wavelength is, for violet, it's shorter compared to the red, all right? Wavelength is a really fundamental property of light, of photons. It's that wavelength that tells you what type of photon it is. And if we're talking about wavelengths in the visible spectrum of light, the photons you can actually see, then they're going to have different wavelengths for different colors, all right? And to kind of give a preview for the last part of the talk, all right, there's this whole electromagnetic spectrum, all right, from low energy to high energy. And within this small sliver, I maybe made it too wide, but within this small sliver, you also have an energy ranking for the visible colors, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. All right, so said in another way, a violet photon has a higher energy and therefore a higher frequency and therefore a shorter wavelength compared to a red photon. All right, and this is something that's good to remember, but I like to bring things back to math when possible. That's something you can see within the mathematical equations. You can see if you raise the frequency, the energy goes up too. If you raise the wavelength, make it longer, you can see how that lowers the energy. If you make a wavelength smaller, you can see how that will increase the energy because a smaller denominator means a bigger number on the other side. All right. And then with the speed of light relationship, you can see that for a photon, if you raise its wavelength, you automatically also lower the frequency. All right, and vice versa. All right, so in this equation, energy and frequency have a direct relationship. They move in the same direction. Here we have an inverse relationship. Energy and wavelength go in opposite directions, and the same can be said for frequency and wavelength. All right, what helps me remember all this, even in case my brain's not speaking math well that day, is I always remember energy and frequency go in the same direction, but then wavelength doesn't. Okay, this is the most simple looking equation, at least to me, so I always start with that. All right. But at the end of the day, that would come out in any calculation anyway. So I'll leave it to you whether to consider memorizing those relationships or not. Okay. All right, but back to defining these ideas of frequency, wavelength, and stuff. So what I did was I drew wave models for a red photon versus a violet photon, all right? And these photon wavelengths can be thought of as like sine functions, all right? Like sine, cosine, due to wave thing, right? Okay. And so what is that wave? All right. I'm going to try to give an explanation at the Chem 101 level. It's not necessarily the most, I hate to admit it, the most important thing to know, but I mean, it's somewhat, yeah, well, I'll let you judge that. All right. So photons have a property called having an electromagnetic field. All right. So even though photons don't have charge, they have an electromagnetic field going on, just like as if they did have charge. All right. And so the photon, okay, we draw it like a wave, but in reality, that wave is actually just measuring the strength of its electromagnetic field, which means its ability to interact with a charge. Okay, it's just measuring its electromagnetic field at any given point in time. So you can see right here, that's the strongest part of the electromagnetic field in this moment, all right, as it has traveled that much. It has the most strength there. And then it reaches a nothing point, and then here, it's the equal strength but opposite, equal but opposite, all right? And this sine behavior, this wave behavior for the electromagnetic field strength carries on until the photon is absorbed somewhere, all right? The main point, especially at the Chem 101 level, is to just observe that this wave property is longer for a red photon compared to a violet photon. That's honestly the most important thing to recognize here. So you can see that I kind of drew out here one complete wave, and it's got to be complete. You got to go through the positive and the negative part of the amplitude. Okay, amplitude, just how much it's sticking up. Fancy word for how much you're sticking up. Right? You have to go through one complete cycle, and our wavelength is from there to there. Okay. And of course, this isn't actually 650 nanometers. I just magnified it. All right. But yeah, we could just pretend this is 650 nanometers. All right. Whereas for a violet photon, that wavelength is shorter. It's 405 nanometers. I prefer to, if I was asked to point out one complete wavelength for a photon, I prefer to go from starting at the bar, the x-axis, I should say, and going like that. And that's what I did there. So I get like a clear positive and negative for the amplitude. For some people, they find it easier to start from the crest of the wave and then go to another crest and then call that one wavelength. All right? It doesn't matter because mathematically, it's the same distance anyways. All right, so you just do whatever makes sense for you. All right, so with some calculations, we can figure out these other properties for the photons. All right, so we're going to calculate for the red photon today. We're going to calculate its frequency. We're also going to calculate its energy. All right, but before we do that, you're like, what's frequency? You didn't do that yet. Okay. So I don't know if you caught on to this, okay? I was giving your brain some time to see this first as I was talking, but from here to there, or heck, we can just go to the end of the page. From here to there versus here to there, I want you to notice that the red photon oscillated less times compared to the violet photon. All right, like on this page, the red photon oscillated maybe about 1.5 times. All right, and then for the violet photon, 1, 2, like 2.25 almost. All right, so that's what frequency means. It means a number of times your electromagnetic field has oscillated in 1 second. All right, so we can see the violet photon is oscillating more. All right, so the violet photon will have a higher energy. And the way I tell my students to remember that higher frequency means higher energy is, this may sound silly, but I just have them wave their hand. And you wave your hand faster, a higher frequency of waving, that takes more energy for you to do. All right, so if you're at an exam and you're doing that, hopefully people, I guess you can't talk an exam, but if you could, you just tell them, oh, I'm just remembering frequency. All right, so let's calculate for a violet photon. And for some of you, that'll probably be enough an example. And then we'll do the red photon afterwards for a comparison. All right, so yeah, let's do it. Let's calculate the energy and frequency of a 405 nanometer violet photon. Okay. So we can do this in any order. The first thing I like to do is I like to write out all the equations involved in light. All right, and depending on your class or your instructor, you may or may not have to memorize these. Okay. So we're first looking for an energy. Let's get energy first. So that narrows it down to these two. And we were given a wavelength. Okay, so that means this one is not going to be used for this problem. All right, I'm going to use this equation because I can put in a wavelength and get out an energy. Of course, our luck is this is the most bulky looking equation, but that makes for a good educational example. We'll do that frequency second. All right, so let's calculate energy. We're going to put in a wavelength, and we're going to get out an energy. All right, here we go. So this equation is perfectly ready to go, actually, because we are wanting the energy. We don't have to rearrange it for the wavelength. So we're just going to be doing some plug and chug. All right. Now, sometimes when I'm teaching this like live, I have us set up the math and then run into the speed bump and then correct it. But I'm going to take a different approach this time. I'm going to address the speed bump immediately. Okay. Recall earlier that I said we might need to use this piece of information. Okay. Notice that we were given a wavelength in nanometers, again, very common for visible light. But these constants, the speed of light works in meters. In order to have correct unit cancellation, we're going to have to convert this to meters. All right, so let's do that immediately. Okay, I'll write out my steps. First, convert nanometers to meters. I'll do some dimensional analysis. There are 10 to the 9 nanometers in 1 meter. Okay, that's 3 sig figs. We have infinite sig figs on a conversion factor, so we're going to have a 3 sig fig answer. Like I've said in other videos, number of sig figs in is often equal to the number of sig figs out, and this is no exception. Okay, now I could do this in my head, but I'll just show the keystrokes. All right, I want scientific notation here. All right, 4.05 times 10 to the minus 7 meters. Okay. All right. That's not the energy yet. We were just doing the busy work of converting. We haven't even done the actual problem yet. All right. Next paper. Okay. So we're still doing wavelength to energy. Oh, there we go. And now we want to actually use the equation. So second, we're going to do plug and chug. All right, so here's our equation. And showing your work is not going to be really fun here because we have 2 long constants to write out. So we got 6.626 times 10 caret minus 34 joule seconds. That's our Planck's constant h. Then we're going to multiply that by the speed of light. All right. And then let's get our denominator. So we did the work earlier. We got 4.05 times 10 to the minus 7 meters. All right. Hopefully you had a lot of fun writing that out. Anywho, so let's keep track of our units. Okay. So energy is going to be in joules. Right, so we're hoping that joules survives all the unit cancellation going on. All right, our meters and our meters cancel out because meters over meters is 1, so that factors out. And then we have seconds times 1 over seconds, All right, seconds divided by seconds. So those cancel out as well. All right, and the only units that survived the unit apocalypse was the joules. All right, so I'm just going to write my joules there as my unit before I forget. And now we can punch into the calculator. All right, let's see. All right, and I'm still in scientific mode, so I got that nice power of 10. That power of 10 is so extreme that it would be a power of 10 in this calculator even without scientific mode. But anyways, so I get 4.9, round that up to 1 times 10 to the minus 19 joules. All right, 4.91 times 10 to the minus 19 joules. And that is our answer for energy. Okay. Typically in a Chem 101 class, I am guessing most instructors will just have you leave it in joules. There is a unit that exists that is smaller than joules, so you don't have to write out all these like really dinky powers of 10. It's called the electron volt, but I gotta keep my class simple, so I gotta hold my tongue and not reveal that. All right, but we're not done yet because the problem also wanted so energy and then a frequency as well. All right, so those two. So did the energy. Now let's go back to our menu of equations. We had E equals h nu. We had E equals hc over lambda. And then we had C equals lambda nu. All right. So we're looking for a frequency this time. We're looking for that one. All right. So that eliminates that from the menu. And we got two choices. We could use this or we could use this. All right. So either would work. In a tie-breaking situation, you can just consider what you enjoy doing more. I'm going to go in a different direction, though. I prefer to use the equation where I can use as much of my original data as possible. Like, if I were to use this equation, that'd be okay. There's the energy. I can plug that in, solve for the nu. But, like, this is already, like, a calculation that wasn't originally provided. Whereas this equation, I can just use the lambda that was already provided, and you've lowered your risk maybe a tiny bit in case you made like an error here. It wouldn't like propagate again. All right. Either way, in fact, I could show it both ways. I'll start with this one. If you're satisfied, you can just leave the video at that point or skip to my final comments. But I'll show that one as well. I have a feeling someone will want that as well. Okay. All right, so we're getting frequencies. We're gonna use this equation, and I'm gonna rearrange it by dividing lambda on both sides. So I end up with nu equal to c over lambda. All right, cool. I think we can do this. So in other words, we're putting in a lambda and getting out a nu. Okay. All right, so I'll just rewrite that equation. Speed of light, c, is 3.00 times 10 to the 8th power meters per second. And we're going to divide that by the lambda that we found earlier. Now, don't put in the nanometer one because that won't cancel properly. So we have to put in the one we've converted earlier. That one. Okay? So we can plug that into the calculator. I always use parentheses for my denominator. Okay, those who have been with me a while know that. If this is your first time watching me, I'll just tell you of that. All right, so there's the answer. 7.41 times 10 to the positive 14 inverse seconds per second, hertz, whatever you want to call it. And that is our frequency. All right. So in the span of 1 second, we had our electromagnetic field, okay, wave, pulse, whatever you want to call it, 7.41 times 10 to the 14th power times, okay? That is a lot of times of it fluctuating, all right, in just 1 second. Okay? An alternative approach, I've shown a lot of dimensional analysis in previous videos, so maybe you'd prefer that approach over this algebraic approach, okay? If you're going to go that way, you start with actually this number, okay? So I'm just going to write alternate dimensional analysis approach. When you do dimensional analysis, you always start with whatever has a single unit, almost always. So what I would have done here, I'll just go to a different color. You just go 4.05 times 10 to the minus 7 meters. And then we need the meters here and the seconds there. So that number is tethered to the meters. So we go like that per 1 second. You can see our meters cancel, leaving up with seconds. All right. And then we would, I don't like what I did here. I should probably edit this out, but then again, I'm just going to leave it in the video. Just, I think it's sometimes good to people see that I make mistakes sometimes too. What I'm getting here, well, I might as well finish the trap I set up for myself. All right, so I got that number. That's a negative 15, and that's seconds. So what I realized midway through is I should have had that at the bottom, which is a little bit unusual, but maybe now you can see why. I ended up with seconds instead of inverse seconds. All right. So what we could have done instead, we could have started with the bottom, or we can just realize that frequency is going to be 1 over seconds. So we can just do 1 divided by the answer, okay, which is the same as doing the inverse function on the answer. I'll just do answer to the minus 1 power. And then we got the same thing as last time. All right, so I am definitely a fan of dimensional analysis most times. I'm sure there's some instructors who be like, use it for everything in chemistry, but I don't know, for me, I think I just made case in point. For me, I find the algebra approach to be a little bit safer here. So you do this if you want, but I don't think I'm going to. All right, yeah, so let me get to the conclusion, and I'll do the second bonus example for those who want it. I imagine for maybe about half of you after this, you'll be ready to turn off the video. Not offended at all. I just provide what people need, as much or as little as people need. All right, so going back to the electromagnetic spectrum, hopefully you're able to get a feel for the scale of things. All right, so we were only working in the visible part of the spectrum today, but there is a whole wide electromagnetic spectrum. All right, we can only see a little sliver of it. So I like to rank it from low energies to high energies. Some books, some instructors like to do it the other way, but that's me. Right, radio waves are the lowest energy. That's used for radios, communication. Microwaves can also be used for communication. That's the way cell phones, work, and Wi-Fi and stuff. They work on a microwave level of signal. Okay, so radio waves, we're talking about like kilometers, really, really long. And then microwaves, we're getting shorter. We're getting more on like the meter-ish scale. I mean, we could be talking like centimeters, millimeters as well. But we're definitely getting like shorter frequencies, wavelengths for the photons. All right, infrared, we're getting even smaller. All right, and we're around, the micro level by now. Okay, IR, infrared. Infra meaning before red. All right, we have the visible part of the spectrum, and the visible part of the spectrum is at the nanometer scale. All right. Little more than nanometers, but basically the nanometer scale. All right, we have UV. All right, we're getting even smaller. Ultraviolet, meaning after violet. Then we have X-rays or Roentgen rays, depending on where you're from. And then we got gamma rays. Okay. Yeah, that's how things go. All right. So, and there's different phenomenon involved, but basically everything up until here involves how electrons move about the nucleus. But then when you're talking about gamma rays, you're talking about nuclear transitions. All right, so that's why gamma rays are often associated with radioactive materials. All right, from a safety point of view, we can divide UV into three categories: A, B, and C. All right, and the cutoff line for safety is a UVA, or maybe about UVA. All right, we can't see UVA, but some of the animal kingdom can. I think like deer and some types of bees or something. All right, UVB and UVC, these are the harmful ones. All right, so if you were to make a cutoff line right there, okay, everything to the right of the cutoff line is what we call ionizing radiation, or ionizing electromagnetic radiation, ionizing photons. All right. The ability to knock electrons off of atoms, and therefore you can create free radicals and do damage. So that's what sunscreen is all about, protecting against UV rays. All right. Now, X-rays, that may bring some fears, like, oh, I have to go get an X-ray, at the dentist or something. The amount of X-rays you're exposed to, generally speaking, are way, way, way lower compared to even like standing outside for a few minutes. And especially technology continues to get improved, so you don't need so many doses. Gamma rays, they can actually be used in super low amounts for like medical diagnostic purposes, but otherwise this is not something you want too much exposure to either. All right. But yeah, that's your a little bit of electromagnetic spectrum in a quick nutshell. There's mnemonic devices online, or you can make your own for remembering the order. I'll give you mine. It's like real Martians. Martians in Venus. And I guess you should be saying on Venus, not in. But remember, I'm not an English major. So real Martians in Venus use X-ray goggles or something like that. All right. If that helps you remember the order. Okay. All right. Last thought before some of you sign off. Okay. I want to give you a sense of familiar numbers when working with photons. Maybe you're able to follow that calculation with me and get some numbers, but it's not something we're used to every day. So speaking for myself, but I think other instructors as well, it'd be my guess for other instructors, and definitely for me, that most of my photon problems revolve around the visible spectrum. Practically speaking, for your average Chem 101 student, that's what they're going to need in their future careers and studies. Okay, you know, if you're like a chemistry, physics, you know, other major, you might need to work with other wavelengths, but and frequencies. But I feel like your typical Chem 101 student needs to be most concerned with visible light. Right. So here's my visible light cheat sheet. Visible light cheat sheet. So when it comes to energy, your answers are going to be on the order of 10 to the minus 19 joules. Okay, and hopefully you saw that earlier already in our violet photon example. All right. When it comes to wavelengths, the waves, the range of photons that we can see is somewhere around the range of 400 to 800 nanometers. All right, this being your violet side and this being your red side. All right, now you may be like, whoa, you wrote those numbers backwards. I thought red was the lower energy. It is, but remember, having a longer wavelength means you're a lower energy. All right. So you go to the higher numbers, you're said to be red shifted. You go to the lower numbers, you're said to be blue shifted. I wish we could say violet shifted, but someone else came up with that term and we're stuck with it. All right. Now, if you're working in meters, you saw that when we converted these values to meters, they were on the order of 10 to the minus 7 power. All right. And then the last thing was a frequency. The frequencies for visible light and maybe even a little bit of like the ultraviolet, but for visible light is going to be on the order of 10 to the positive 14 inverse seconds. All right, for those who are going, take care. Thanks for tuning in. For those who wanted to read photon calculations, we can do that too. All right, so red photon this time. All right, so for the red photon, we had a wavelength of 650 nanometers. All right, and I'm going to ask us the same questions. Let's get an energy, and let's get a frequency. Okay. To be a little bit different in this example, oh, now I'm on the page. To be a little different in this example, I'll have us go for the frequency first. Okay. So, write out your menu of equations. You know, if I was in your shoes, I would just try to do this independently at this point and compare with my answer. So yeah, I'm inviting you to skip through my video and then just see the end result. So I'm just gonna leave the camera on and just work this out. All right. So I got a wavelength. So I don't want that one, this one, or that one. And I said I was going to get the frequency first, so I'm going to do that one first. Okay. convert that. Frequency, done. And then let's do an energy. Okay. I would normally choose this one because lambda was the original info they gave me, but I'm going to show you that doing this one would also be okay. All right, H. I'm just using the previous answer on the screen instead of retyping, and then multiplying it by the Planck's constant. All right, there we go. So, yeah, just to show you that I wasn't making stuff up, we can compare the violet versus red photon. Okay. And if you want to like write a symbol for photon, you want some shorthand. Some people will write like h nu, because that's how you calculate the energy of a photon. So the red photon, the red h nu versus the violet h nu. All right, so let's see how we did on energy. Let's see how we did on frequency. Let's see how we did on wavelength. And then you could get like a trick question. How about the speed? Remember, the speed of all photons are the same. It's just the speed of light of 3.00 times 10 to the 8th power meters per second. All right, so for the red photon, 3.06 times 10 to the minus 19 joules. Okay. Whereas for the violet photon, that was a couple of slides back, wasn't it? All right, 4.91 times 10 to the minus 19 joules. Okay. All right, so violet won there. And then let's go on to frequencies. We had 4.62 times 10 to the positive 14 inverse seconds. And for the violet photon, (7.41 times 10 to the positive 14 inverse seconds. So violet is the bigger number there. Okay, the wavelengths were already given. Okay, and lower energy means longer or bigger wavelength, if that helps your mind. All right, so there you go. All right, longer video, but I wanted to give enough stuff so people could sort through and get what they needed. Hope this helps. Give any comments or suggestions. Otherwise, have a good day. See ya. Oh, there we go.